Hello and welcome to another video. In this video we're going to be working on Freedom Trail. And in this one you have some game, so I'm not going to talk about this whole thing, but basically I'll explain it. So you have a string, and it's a circular string. So you start at this character, and then you also have a key. And your goal is to press every single button of the key, so the character of the string has to match the key. And to press the button costs one operation, and then you also have to traverse the string to get to the same character as the key, and the string is circular, so that's kind of how they show it here. So in this first example, is gauding, you start here and it's circular. So it's gauding, and then it goes back to 0, so you can like go in a circle. And so the characters you're looking for is GD, so you start here. So you're already on the G, so you can just press it right away. That costs one operation. And then you need to get to D, and so to D would take 2 operations, and then the actual pressing of the button, so that would be 3 more. So it's going to be 4. That's kind of the idea here, is you have a string, it's a circular string, you start at 0, and you can move around like this. So this problem, honestly, there's like 50 optimizations, and I'll talk about most of them, and I'll show you different code solutions in different languages. They can definitely be improved, but this is a really good one to, if you want to practice DP or a keep. This is going to be a good one, and I'll kind of show you both solutions there and like a bunch of optimizations. So the first thing you can do is just kind of like the almost brute force solution is whenever you're at a character, like, so first of all, you should be able to recognize that, like, if you're at a character and the key you're trying to press is that character, like if your character's matching already, right? I'm at this character, I'm trying to hit this character, then it's pretty easy. I just hit the button, right? But what if I'm at like this character and I'm trying to get to a G, let's say. So you basically can go forward or backward and figure out like what's the longest it can take to get to a G. And the way to do that is like the brute force solution. Let's say you're here. You would just say like, okay, let me go forward as far as I can, and then let me go backward as far as I can. And every G I hit in either direction, I'll recurse to those. Right? So I guess, yeah, let's say you're here. You'd be like, okay, let me go 1, 2, 3, 4 steps. Or let me go back 2 steps. And I'd recurse to both of those. And so you can do a DP solution here. And like, what state do we need to have? Well, we need to know like where we are on the ring, right? So index on the ring, to know like what character we're currently at. And then we also need to know index on the key. And once we know both of those, so this would be our state, then our base case is pretty easy. We just are out of bounds on the key, so we just return 0. That's pretty easy, right? Like we don't need any more operations. And our recursive case, so this is like the brute force recursive case, try to go recurse to every single letter on the key or on the ring that matches the key. And pretty easy, you just have some index, right? So like I said, let's say you have some string like this. Let's say you're at this I, and you will basically go forward all the way. Like let's say you're looking for a G, you'll go forward all the way, and every G you hit, you will write down how many steps it took you plus hitting the button. And then your new ring location will be, sorry, you're actually over here. So let's say you're trying to hit the G here, you're here. Your new ring location will be wherever you end up, and the steps is just the distance. So you go forward all the way, and then you go backward all the way. And that will cover the entire thing, right? That will cover every single G. And you could do that, and that is going to be, so time complexity wise, so for our state, we have an index on the ring, let's call that R. We have an index on the key, let's call that K. And then every single time we're looping through the entire string, so that's R again. So we have R squared K, and that will pass. And then our space would be RK here, I believe. So that would work. But there's a thing you can recognize, and I don't think it's too hard to recognize, and it's the optimal solution. Basically, now even if you recognize it's not easy to do still, the optimal solution is never going to require you to go past a certain thing. And what I mean by that is like, let's say we're here. Let's say we're at this O, and we're looking to go to a D. Well, once we hit this first D, we're never gonna want to go to the second one. That's never gonna be better. It might be the same, but it's never gonna be better. Because if you look at like, let's just look at an example. So let's say we're at this index, and the character we're trying to go to is like here, here, and here. So if we go here, this is strictly going to be longer than here. And no matter where, like, let's just think of like where the next character can be after this. So if the next character, like after this one we're going to, is over here, then we're basically, in order to get to the first character and the second character, we're gonna have to go like this and this, or this and this, which is the same distance, right? So if the next character is over here, it's the same. If the next character is over here, let's say, then you're gonna go here and then here, or you're gonna go here and here. And the first one's clearly better, right? You take one less step. So, and so on, right? So basically, if the next character is further down the road, it's worse, or it's the same. And if the next character you have to go back, then this one was better. So you're always going to want to go to like the first right number that you find. And the same thing for the left. You're always going to want to go to the first left location that you find that matches what you're looking for. And so it's kind of the same thing. So now you can simplify to find closest left and right letter from where we are. And like, obviously, if you traverse a string in both directions, you can do that pretty easily, but can we speed this up? And this is like the tough part. And basically you can speed this up. So instead of traversing the string every single time, we can just store indices where, so we can have a hash map of every letter in the string and the indices where it occurs. So for example, let's say letter A. Let's say a string's length 100 and letter A occurs at like 5, 15, 55, or something like this. Oops, so it's like this. And we're on index 10. Not 10, let's say we're on index 30 or 32 or something. So we can just binary search through all of the letter A's that we have stored now. Even if you don't binary search, it's just faster to search through the array of A's, right? Like you don't have to search through the whole string now. You can just search through the letter you're looking for. But you can also binary search, because like what if your whole string is A's? Right, like this. Then you just have every location. So you can binary search in your string for index of first letter greater than my current index, and index of first letter less than my current index. And so in this case, the first index greater would be 55, and the first index less would be 15. And so this is what you'd kind of find. So the optimal solution is always just gonna, at least I think, I don't think you can just go one way. I think you have to try the closest left and the closest right. I might be wrong on that. Like there might be a way to do it where you only need one, but I thought of some cases where you might need two. For example, let's say you're here, and you're looking for a G. So if you go left, you're gonna go here, but if you go right, you're gonna go here. And then if your next letter is like an O, this distance and this distance is the same. It's both 3, but the optimal solution would have been going right. And similarly, if you're trying to go to, instead of the O, you're trying to go to the N after that, then this one would have been better. So I think there's like some things like that you're going to want to get the leftmost and the rightmost closest to it. But essentially, so what you can do is, so you can, for every letter, you just store an array of where it occurs. And then given an index, you just binary search in your array to get the index of the first letter greater and the first letter less. And that's just like a basic binary search. So I'll show you the code in like a few languages for that, but it's not that hard. Like I ran 2 binary searches, and then I think I have a Python solution where I ran 1 binary search, but then I looked at my code and it's kind of hard to follow, to be honest. So, but yeah, essentially, that's kind of the idea here, is we can quickly, like if we're at some index and let's say we're looking for G, we can quickly look where do all our G's occur and binary search for both sides. But so when we pick 32, we did actually have an and both sides, but what if we don't, right? So what if we're at index, let's just say 70. Then where would we want to go? So I think actually here you can pick one, but I ended up picking two. But let's say you want to figure out like what's the first one I get to going right. So the first one you get to going right, if your number is greater than this whole thing, then if you go right, you just start out at the start again. And so you wouldn't binary search that one, you would just say that. And then similarly, if we're at index 1, what's the first index we'd get to going left? Well, we'll just loop around and we'll end up here. So you could check for those things. Like if the index is greater than the whole thing and you're going right, then you're going to go over here. If the index is less than the whole thing and you're going left, you're going to go here. But basically, it's kind of complicated. I'll show you the code. I'm sure you can get rid of a bunch of stuff that's unnecessary. And, you know, if you guys can think of some stuff. Because I think the only times you need both is if it's a tie, I think. I haven't really thought it through, but I know for sure that like going left and going right, the optimal solution is never going to involve going more than to the first one you find. But anyway, so if you binary search now, so instead of like looping through a string to find where a character is, we can just have a function that will binary search through all the locations of our letter, and we'll just return the index of letter to the left, as long as the distance there, and the index of letter to the right and the distance there. And then we basically just do the minimum of those. So we say like, okay, we have to travel this distance to go here, this distance to go here, plus 1 for pushing the button, and then whichever one gives us the minimum, we can DP that. And so that solution will be, so the state again is the index on the ring, which is R, the index on the key, which is K, and the binary search, which is log of R. So we save, instead of having an n cubed, basically we have like an n squared log n. And you can also bottom up DP this, which I didn't do, but because basically every time you recurse on the key, you're just going to the next thing on the key. So you can bottom up DP that, and then you will have an R, I think it's just R space now, because you'll get rid of this key dimension. So let's show you the Python solution for kind of what I was saying. So basically this find moves is like this binary search where I'm finding the closest letter to the left and the right. It's kind of confusing, to be honest, and I don't even remember what I did because I did one binary search. I think it's easier to do two. I think with two it's pretty straightforward. But yeah, basically your DP function, it just says if you're out of bounds, you're done. If the actual thing you're looking for matches exactly, then you just push the button. Otherwise, calculate this whole thing, right? How many moves it takes to go left, how many moves it takes to go right, where's the left location, where's the right location, and then just do the minimum of those two. And that's essentially, and you can do this bottom up, and you'll get rid of this this cur thing, or not this cur thing, this key position, because the key will just increment by 1. It's probably pretty hard to code, but you can do it if you want to. So that's that. Now, you can also do this with a heap. And so basically with a heap, instead of doing like the DP solution, we're just going to store 3 things. So we're going to store distance, as always, in a heap, right? Because the heap is usually like stored by the distance. And then we store our location on the ring. Let's call that R. And then we store the location on the key, which is K. And so if we get to the same thing twice, like for example, if we were looking for this letter on the key and we're here on the ring, if we visit this again, we never want to do that, right? Like that's redundant. So we can also have a visited set, visited, or you can use an array or set or whatever, that's going to have tuples or, you know, array of RK. And then if you visit this again, that means this is no good. But essentially, you just have a heap of distance. And then basically what you do is, like, let's say you're at some node. Let's say you're at this node. So this one's going to be pretty easy, right? Because these two match. So when these two match, all you're going to put in is you're going to say, okay, that distance is 1 because I just need to push the button. And then I'll be on this same thing on the ring. So this will be 0. And then I'll be on this thing on the key, so 1. But now what do we do, right? Now we're on this letter. So how do we, or actually no, we're not on that letter. We're on this letter on the key. So we're on G, we need to get to D. And now this is where you would call that binary search function that gives you the shortest distance to the left and the shortest distance to the right. And so here, if we're on, let's see, this G. So the shortest distance to the left is going to be this way. So 1, 2, 3 over here. So this will be distance 3. You add it to your old distance, so it'll be 4 total. And now we're on, so if we go left, remember we're going to go around this way and we're going to come over here. And this is index 3. And then we'll be on, we're done with the key there, so we'll be over here. And then the short distance to the right is going to be 1, 2. So it'll be a total of 3. And then we're on this index over here, which is index 2. And then we're done as well. That's kind of the idea. So at every single letter, you just figure out short distance to the left, short distance to the right. And so the maximum possible states here that you can visit is r times k. So this is going to be space r times k. And the runtime is going to be, so it's going to be r times k times, so essentially you're doing a binary search every time. So that's like log of the distance of r. So log r. And then also you're doing a heap hop and a heap push. That's also log of however many things you have on the heap. And I think that's like, I guess it's like the number of edges. So the most edges you can have is like, you basically have an edge from one node to every other node. Or you don't have an edge from one node to every other node. You can have an edge from like one node to every other letter. So that's probably like 26 times r or something. So I think it's something like, I think, I could be wrong about this, but I think it's something like this. This might be k instead, but roughly like this. So it's basically rk and then like log of both of them. Something like that. Could be a little bit wrong about that. It's kind of hard to like figure out the exact heap one. But yeah, that's kind of the idea. So this is super confusing, but this is a really good one if you want to try to do bottom-up DP, or even just the regular memoization, but with this binary search optimization. Because the binary search optimization isn't that easy, and that's probably the hardest part of the code, I would say, is like for every letter, find the closest letter to the left and the closest letter to the right. And like getting the math right? Like, let's say we're on this letter, and, you know, the closest letter to there's only one more letter. So like, how far would it go? How far would you go if you go right? Like, you'd have to loop around and calculate that and so on. I do think though that if there's only one letter, you probably just always go left. At least I think, and that might be the best thing. And I think you only have to go both ways if there's a tie. I could be wrong there, but I know for sure if you go both ways, it'll work. So definitely kind of confusing. So let's take a look at the Java code, and it's super long, and I definitely could have made it better. But this is a pretty tough problem, to be honest, if you use all these optimizations. So we have like our R and K, and we have our, so like I said, for every letter, you're going to store a list of all the locations where it occurs, so you can binary search through that. Even if you don't binary search through it, you can just store a list of all the locations it occurs and do a normal search. It'll still be faster. But obviously, if your entire word is like this, then that's where the binary search will perform much better. So you just do that. So we make a visited array, we make a heap, and then we add 0, 0, 0, right? So the distance is 0, and we start at location 0 on the ring and location 0 on the key. And then we keep getting this thing off of it, and then we check. If we're done with the key, then we just return the minimum distance it took from the heap. If it's visited, we can continue. Otherwise, we can mark it as visited. And if the value on the ring matches the value on the key already, then the optimal thing is just to not move it at all. Just push the button right away, so that you just leave everything the same. Over here. You leave everything the same. It just takes one more distance, and then you move up on the key. Otherwise, you have to do this whole thing. So you take the left location you end up at, the left distance it took, the right location, the right distances took, which is this function that I'll show you in a little bit. And then if you haven't visited that, then add that to your heap. And so this is pretty long. I definitely could have like made this better, but essentially you just take your current location, you take your destination, you take your locations, and you take the length of the ring. Then you figure out where you're at, and this is what I said. So if you are trying to figure out how long it takes to go right, let's say, but you don't have anything to the right of this, then the distance is just this. So you can just calculate that in O of 1. Similarly, if you're trying to go left, but let's say you don't have anything to the left, the distance is this whole thing, which you can calculate in O of 1. Otherwise, you just run two binary searches to figure out like what's the closest left one, what's the closest right one. And so that's what I did. It's like a decent amount of duplicate code. Definitely could have cleaned it up, but there was kind of a lot, so I was like, it's fine. So essentially all the same kind of thing. You just do a binary search to figure out the closest for both. And then you get this left distance, right distance, and then now you return these 4 things. So the left location you end up at, the right location you end up at, the left distance, and the right distance. And yeah, and this is pretty fast, I think. Definitely, probably the hardest problem I've coded so far in Java. It's like, even if I made it a little short, it's still pretty long to do all these optimizations, which is kind of insane. This is the point where if this was like a contest, I would rather do this in Python because I could do it in like a fifth of the time, to be honest. Like Java is just like, this is where the issues with Java come in for sure, when the code gets kind of long. But once I get used to it, I think it'll be fine. I just have to think about it a lot more. So essentially, yeah, the time for this one. So I think the time for this one is actually going to be like this, because I think the most states it can ever have is the number of items on the ring, or the length of the ring times the length of the key. So I think it's like R times K, and then to do a heap pop and a heap pop and a heap push. If this is the length of the heap, then this would basically be like n log n, where this is n. So I think it's like this times log r times k. I think something like that. And space is r times k. So I do think bottom-up DP is maybe a little bit faster, but it's kind of getting to the same point. The main thing is recognizing this, and this would be a lot more relevant. Like I do think this would be like a pretty good, to be honest, like very hard LeetCode contest problem if they, instead of making this ring length like 100, they can make it length times like 10, like they can make the length of this like 10 to the 5th, and then that would really force you to do the binary search. I think that would be like a pretty solid problem. Yeah, small change there, and then with that, if you did the binary search, it would pass, and if you just did the brute force run through the string, it would fail. So yeah, in this case, you can kind of do whatever you want. So hopefully this is helpful. Pretty long, and I know the code is super long, so I'll post these. Yeah, I didn't want to like code the code from scratch because I think it took me like an hour or something to write it in Java, so that would just take forever. But yeah, essentially you kind of get the idea, and this is, like I said, this is a very good one to actually practice the coding, because it's, even if you know what to do, you can go back and review everything I said and figure out, okay, how do I actually implement each section here. And yeah, not easy. And I think that's like a sign of a good problem, is even if you know the exact solution, it still takes you 30 plus minutes. Like, and if you haven't done too many LeetCodes, like I pretty much told you the exact solution, it still probably will take you like an hour. So good one to try yourself. So hopefully it was helpful. If it was, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.